Are you considering switching over to a heat pump? If so, I'm going to give you my example of what I did. Um, I was looking to change out my AC anyways, so it seemed like a good time to do that. I mean, I wouldn't have gotten a rebate on the AC, but I am getting rebates on the heat pump, big ones. But I'm not going to really discuss the rebates too much. I just want to go through what I did and how it all worked out. Let's crunch some numbers. Okay, so this is the equipment that I purchased. I purchased the Mitsubishi, obviously. This is the outdoor unit here. I also purchased the IntelliHeat coil, which fits right on top of my Gibson KG6 furnace. I purchased a B cabinet. These come in B or C. I purchased the B right here, which is a little smaller than the C, but it fit well on top of my Gibson furnace. Um, just remove the A coil, my original ACA coil, and pop this on, and off and running. These are some of the specs. Just I cut and paste just a few of the specs that matter, not all of them. It's at 47 degrees outside, has an output of 38,000, well, between 38 and 43, and an input of 3.5 kilowatts or 3590 watts. Um, that's that. At 17, it's putting out 29,000, which is great. And it's got an input of 3180. Now there's not a big difference between 3180 and 3590 input. So you kind of use an average between these two, but that's why I built a spreadsheet. So it can calculate all the different inputs at different times. Here we have the outside unit. It's really dark down here, but this is the IntelliHeat coil. That's the control box there. That's the user interface. Come around here. It's so this is stacked on the coil is on a Gibson, I don't know, KG6, which is 95% natural gas. So that's it. See sensors for the coil here. There's sensors going in with the line set. This thing is awesome. Okay. Taking a look at coefficient of performance. You can see a COP, coefficient of performance, at 47 is 3.1. That means that for every unit of input, I'm getting out 3.1 times that. So basically my output is 38,000 at 47 degrees. And my input is 3590 watts. So if we take 3590 watts and turn that into BTUs, which is times 3.412, it's 12,249 BTUs. That divided into the 38,000 output is 3.1 COP. It's that's why we call it a magic machine. Okay, so like I say, I built a spreadsheet, and so that I can really look at all the different temperatures and see where my savings would be, this and that, and how far I could run down the heat pump. So I know my the BTU output of the equipment at 35 degrees is 34,568 BTUs. And now if I can now change this number to see what it'll be at, something different. So let's plug in 17. 17, it changes this. Now the spreadsheet uses these numbers to calculate savings or cost at different temperatures. Which you have to do. If you don't do this, then you don't know where you are. And you have to know what your heat loss is of the house or the building. Otherwise, you're just making wild guesses, So, at 17 degrees, well, yeah, we'll go to 21. 21, my equipment is outputting 30,500. So we'll put this one also at 21. And I know my heat loss is 30,450. So basically I've already gone through this, and I know that now my equipment will not be able to carry the load below 21 degrees. I know that. So when I set my economic balance point, I want that to be at a point that is lower than that, because I want my equipment to work down. I want it to be able to do everything it can do before I switch over to natural gas. So we know here it says, below 21, the equipment can no longer keep up, blah, blah, blah. The equipment will automatically switch over on its own. It has that technology built in. If it can't keep up with set point, it's going to switch over. And that, in my opinion, is going to happen at 21 degrees. Let's see what else. Yeah, okay. So for me, natural gas versus the heat pump. Where is the cost? What's going to happen? Where is it most efficient? So for me, I know that I'm paying $2.60 per therm per 100,000 BTUs of natural gas. And my efficiency of my equipment is 0.95, which is also a COP of 0.95. So if I'm putting in, I'm paying for 100,000 BTUs, but I'm only getting a usable 95,000. Now, I also know that I spent, I purchased 850 therms last year of natural gas to heat my house. I only, but that was only 808 usable therms at my efficiency. So now I can use that number to try and match my heat pump. I know my heat pump has to put out an equivalent of 808 therms in BTUs. So let's look at that. Now I know my cost of electricity is 17 cents per kilowatt hour. I plug this in, and all these gray squares are, the spreadsheet calculations to figure it all out mathematically. If we don't figure this out mathematically, there's no point of it at all. Anybody can say it doesn't work below a temperature, but the math tells you everything. So right here, I know that my heat pump has to run 2,642 hours to achieve 808 usable therms of gas. And then the spreadsheet calculates the cost difference. So for electricity, it's costing me $15.20. For natural gas, it's costing me $2,210. And the difference is $690. That's at 21 degrees Fahrenheit. So we could change the number in the spreadsheet to whatever we wanted. If we changed it to 35, change it to 35, obviously the cost difference is greater, because it's not quite looking, it's just telling me what I saved, but this part didn't calculate in the extra cost I used on the natural gas. So you have to figure that out. You have to put in a, where it switched over to fossil fuel and how much time it spent using fossil fuel below that point. So, obviously it's going to spend more than 10% of the time under 35. So that would be a lot higher. It's going to, that'd probably be 30%. So we're going to go back to 21 degrees because I know that's my switchover point. At 21, I'm saying, oh, how much time is it spending below 21 here? Probably 10% of the time, because the average temperature in this area is 40 degrees. I don't think we're going to, as far as the winter heating months goes, maybe 10% of the time it'll be under 21. So in that situation, that makes sense. Also, in addition to that, we have to figure out what percent of my savings will be gained by running high efficiency air conditioning now. Because I had an old R22 unit. I'm definitely going to save 15% during the summer by running this heat pump. Maybe more. I'm not exactly sure. I can, like I say, I can tweak these numbers at any point as we go. But with this situation, my actual cost savings are running the heat pump down to 21, and the savings in the summer is 724. One more thing you got to calculate. Oh yeah, I could change that number. Let's say I change it to 20%. 655 is my savings. So if I said, 20% of the time it's running at 21, that changes the number to 655. Back to 10, 724. Anyways, one more thing we got to figure out is what amount of additional cost was incurred by the purchase of my heat pump versus a conventional system. All I was going to do was replace the AC. What would that have cost? And I wouldn't have gotten any rebate. So I had to spend that money anyway. So what is the difference by putting in a heat pump? To me, and subtracting your rebates and all of that, what is my cost difference? I'm saying $2,000. But it's really not even that. But I put $2,000 in there more just to show how quickly my return on investment would happen. And that's 2.9 years, so obviously to me that's a no-brainer. Why wouldn't I do it? But the one more thing in my system that makes this all work great is I'll show you right now. So this is to me, the key that makes this whole heat pump work for me is that I have 9.3 kilowatts of solar on the roof. And right now I have basically no electric bill. In fact, I have a negative electric bill. So I'm just going to tweak my usage a little bit more and tighten up on some other things to help, go towards the heat pump, which is going to add extra power, obviously. But I won't be paying for natural gas, hardly. So it's all going to work out. Yeah, so that's it. I'm going to be monitoring the power, as I go, just to see how well it really, truly works out in real life. And have a great day. Thanks for watching.